So in this problem, we are given a traffic light hanging from a set of ropes, and we are given its force, its weight, realizing that weight is in newtons. Now, it's not its mass that we're given the force of gravity or its weight. And it identifies that we are supposed to find all three tensions. So let's first draw a free body diagram of the traffic light. We have 500 newtons pulling it down from its weight, and we have T3 pulling it up. Well, we know when we're working with free body diagrams, we want to do net force equations. And we know that this traffic light is not moving. A lot of these problems are actually something called statics. And it might not be explicitly said to you, but when you're looking at something like a traffic light, right, these ropes aren't expanding or contracting like a spring or a slinky. It's a static, not moving situation. And whenever there is no motion, all the net forces add up to 0. So whenever there's no motion, net force is 0. No acceleration. Once we know that, let's see, we can start saying that 0 is equal to, well, adding all the forces. And T3 goes up in the positive direction. 500 is negative because it goes down. And so we can find by adding 500 to both sides that T3 is just 500 newtons, right? There's only the two forces acting on the object, so they have to be equal. And now we want to move on to our rope interface, where all the ropes meet. And we're given a couple of kind of nasty angles. And by understanding complementary angles, we can actually rearrange these two angles down here, sort of thing, like 41 there and 63 there. Because these two lines here, these two are parallel. And so from geometry, we were able to make sure that those two angles were equal. And that sort of makes drawing this free body diagram just a little simpler. And now we are going to take the net force in the x and y direction, and it's all equal to 0 because there is no motion. And so this is going to be T2, and this is T3. So the x direction, right? T2 can be our first force, and it points in the positive x direction. So we're going to have a positive component, and it's going to be the magnitude is going to be sort of our x component is the magnitude hypotenuse kind of thing, T2, times either sine or cosine of 63. And we know it's cosine because we're looking for that adjacent side. Cosine is adjacent over hypotenuse. And so we know we're using the cosine instead of sine. Our next x component is going to be from T3, which is actually negative T3, because it points to the left in our negative direction. And once again, we want that adjacent side on the bottom, so we're going to use cosine of 41. Our negative 500 newtons pointing straight down has no x component, and so we can just sort of leave that off. Now this equation has two unknowns, T2 and T3. We can actually just keep going and take the net force in the y direction, and we're keeping in mind that the number of variables we have takes that number of equations to solve. So if we have 2 equations, we can solve for 2 variables. If we have 5 variables, it's going to take 5 equations to solve, right? So we can't solve both of these variables with one equation, but net force from the y direction is going to give us another equation, a second equation. And all of a sudden, now we're going to be able to solve both variables. And it's going to be a little bit tricky. The algebra is going to be a little confusing, but we are going to be able to find a number for all 3 tensions, right? And looking at the y-axis, we see all 3 forces generate a y component. Let's start with T2, right? We're looking for the y component, sort of chunk there, and that's going to be the hypotenuse. And now we're going to be working with sine of 63 for that opposite side. Plus, let's go to T3. T3 also points up in the positive direction, and we want its y component just as with T2. And the last thing is 500 newtons points in this direct negative down direction. And so all we have here is two equations and two unknowns. And we can actually go ahead and solve what T2 and T3 are. The first thing I'd recommend doing is taking this equation and doing just a little bit of algebra on it. What we're trying to get is either like a T2 equals or a T3 equals, because that will allow us to substitute this T2 equals into our second equation. And all of a sudden, we're only going to have one unknown variable in that equation. So our first step was just moving the T3 term to the right side. And then we can divide by cosine of 63 to find that T2 equals T3 times the ratio of cosine 41 to cosine 63. And we can plug that into this equation there. Doing so shows us that we have T3 times sine 63 divided by cosine 63, and also we have this cosine 41. So this can be a little confusing. We're sort of getting a little garbled up. What we're really just doing is replacing these three terms into T2. Sine 63 remains in the numerator. Cosine 41 is in the numerator. And we have the division by cosine 63, keeping in mind that multiplication is commutative, or you can move things around however you want. And for us, we're going to want to get this sort of constant out here by itself and separate T3 a little bit. Right? And we have T3 times sine of 41. And we're going to add 500 to both sides, so you can put that on the other side of the equal sign. And now all we have to do is, well, we can combine like terms. We get T3 equals sine 63 times cosine 41 divided by cosine 63 plus sine 41. Being careful to keep all of that in one set of parentheses so that T3 is distributed. And we can divide both sides by this sort of sine and cosine chunk, by that whole term. Sine 63 times, whoops, that's not right. Sine 63 times cosine 41 over cosine 63 plus sine 41. And so writing that all out, we end up finding this fraction for T3, and we can plug that into a calculator. And we find T3 to be 233.9 newtons. Now we found T3, and remember above we actually found whoops, we made a mistake. We accidentally wrote T3 in two places. This one down here was supposed to be T1 for all this work. My bad. So to remedy that, we are going to instead change this 3 this is going to be T1. So that one shows up less, and it's a little easier to fix. So that's going to be our T1 now. We should be very careful we don't use T3 in two places. That's very bad. It's my mistake. So now we have an expression for T1. We know what T3 is, right? Looking at this picture here. We can find T2 now by going back to this equation, this one here, right? So if we plug in T3, let's go down here. We can find, here we can go right here to this equation, this one we found here, where T2 is T3, which was 233.9 times cosine 41 over cosine 63. We can just go ahead and plug that in the calculator. And that tells us that T2 was 388.9 newtons. And so we have found the tension in all 3 pieces of rope. And we did it by taking the free body diagram of the light with the tension and the gravity force acting on it. But most importantly, we took the free body diagram of the point where the ropes meet, that sort of joint. We can take the free body diagram around that point, and that relates all 3 tensions together. We take the net force in the x and y direction, and we can figure out what all 3 tensions are.